This problem reads, a communication satellite is in a synchronous orbit that is 3.6 times 10 to the 7 meters directly above the equator. The satellite is located midway between Quito, Ecuador, and Belém, Brazil, two cities almost on the equator separated by a distance of 3.5 times 10 to the 6 meters. Find the time it takes for a telephone call to go by way of satellite between these cities. Ignore the curvature of the Earth. Alright, so I looked them up on Google Maps, and here's Quito, and here is Belém, and here's a scale, so 200 miles, 500 kilometers, and you can see, well, they're on the same continent, but they're still 3,500 kilometers or 2,200 miles apart from each other. What I thought was kind of interesting is that the name for Belém is quite a bit bigger than the one for Quito, even though this is the capital of an entire country, even though it's a small country, Ecuador. And then I looked it up. Well, Quito has basically the same population as Belém, both of them 1.4 million people. And yeah, I'm not sure why this one name is here a little bit bigger. It's the capital of a province of Brazil. Anyway, so that's on Google's map. And then let's see how we do the problem. I had already done this, and then I noticed when I was done that with what it says in the book here, 36,000 kilometers to the satellite and 3,500 kilometers between the cities, that I accidentally swapped the digits. So now I'm correcting that, and this is actually a second recording. That's why everything is already there, what I meant to draw in while I'm recording. Okay, so here's the distance of 36,000 kilometers to the satellite, which is roughly five and a half times the radius of the Earth. And it bisects this kind of triangle. If we assume that Belém would be here and Quito would be here, then this here would be a triangle such that could be bisected in two triangles of equal size by this distance here, 36,000 kilometers. And to figure out what the distance is that the radio signal would have to travel is, of course, the hypotenuse of this right triangle, with this one here being half the distance between the two cities, which is 1,750 kilometers, half that distance. And of course here the same thing. So for the hypotenuse, then I have this expression, and then because it has to travel this way and back, that's where the factor 2 comes in, of course. I wrote it all in kilometers. It's just nicer to do than, for me at least, than to have it in meters with the scientific notation. So here it is. You're going to come up with kilometers. It's going to be in the neighborhood of like close to 80,000 kilometers and so on, and in that neighborhood. Then divide that by the speed of light. That would be 300,000 kilometers per second. I wouldn't use 299,975 kilometers per second because it's already two significant figures. So 300,000 kilometers per second is just fine, and you come up with this one here. And then roughly 80,000 kilometers divided by 300,000 kilometers per second gives you in the neighborhood of like 0.2 to 0.3 seconds. And in a broadcast like that, or a telephone conversation with somebody, you would actually notice that there's a strange delay, that fraction of a second. You say something and it takes 0.2 some seconds to get to the other side, and then the response also takes 0.2 seconds to come back. So it's kind of like half a second there until you get the response after you're done saying something. Alright, actually that's basically it. That's really the problem, and I showed, of course, a couple of more things here, where they are on the map. I also looked up geosynchronous satellites, and this is how they would look like. Geosynchronous satellite orbits the Earth in exact the same time that the Earth needs to rotate for one rotation. And that is not 24 hours, it's exactly 23 hours, 56 minutes, and 4 seconds. That's how long the Earth needs for one rotation. The remainder, approximately 4 minutes to make a full 24-hour day, come in because the Earth at the same time is also orbiting. But for geosynchronous satellite to stay in exactly that same spot above the Earth, would mean 23 hours, 56 minutes, and 4 seconds. It also means a particular distance that is fixed by Kepler's third law, which relates the distance of a satellite to the time it needs to orbit, and distance cubed over that time squared. And there's only one such distance, and that is that 36,000 kilometers that is mentioned in the physics problem. 36,000 kilometers altitude, respectively, roughly 42,000 kilometers from the Earth center. There is no other distance. Now, you could say, well, that's not a whole lot of satellites that you could put there, but you have this huge ring around here on top of the Earth's equator, and there's a lot of satellites that you can place there, and I'm sure there are hundreds, maybe even thousands of satellites that are currently situated there. Yeah, giving us this geosynchronous network for communication. I've got one little thing to mention earlier. They say in the problem that we should neglect the curvature of the Earth, and really the reason why they're able to say that is because with the curvature of the Earth, it gives us a little bit extra distance here, but it's going to be small compared to the total distance of 36,000 kilometers. So even if we went to the effort of actually including it, which would be some calculation effort, it would hardly change anything of the total time that we would get. I mean, it would be really in the neighborhood of like a few thousandths of a second. And so they say, don't go to that effort. The simple Pythagorean here times 2 divided by the speed of light will be just enough. This is then for the next problem. Michelson set up for measuring the speed of light with the mirrors placed on Mount San Antonio and Mount Wilson, California, which are 35 kilometers apart. And that's what this illustration shows. Using a value of 300,000 kilometers per second for the speed of light, find the minimum angular speed in revolutions per second for the rotating mirror. And looks like I like Google Maps, so I have Mount Wilson over here, and this blob up there shows Mount San Antonio, and these two are apparently 35 kilometers or 22 miles away. My scale is just out of the picture. Down here it is 2 miles 5 kilometers, and I guess this must be the northern parts of, well, is it Los Angeles, or yeah, I think it is Los Angeles, right? Because this confused me as San Antonio, but it's in a different state anyway, right? Anyway, I'm diverting myself here. This is what it is about. The distance between Mount Wilson and Mount San Antonio. And what Michelson did with that is he tried to measure the speed of light very accurately, and he needed to have a long distance so that with what was available to him around the year 1900, he could measure it pretty accurately. And the longer he takes the distance, that's just one measurement that he is going to have available to him more accurately, and it takes the light longer to go from the light source to the eye, to the observer here, and then determine the rotations of this one and figure out, well, how fast is light actually. All right, so let's see how this works. Here's the light source. It hits the mirror and is reflected to this fixed mirror on the other mountain, goes back to this octagonal mirror, and then hits the observer. Now, if this was not rotating, it would be straightforward, and we can see that. But if it wasn't rotating, it wasn't yelled anything. Turn the light source on, and you get it. It's there. Now, when you rotate it, notice that when it hits and goes over there and goes over there, and if it's not in sync with that, it will just reflect somewhere else, here or there. If it just doesn't have the right number of revolutions, it will go somewhere else. So the way this would work is rotate it in such a way that when the light source hits and then comes back, by the time it comes back, this surface here has now rotated to become this surface here exactly, and the observer can see it. So that's the basic idea behind that experimental setup. And then from determining what the rotation is, calculate backwards what the speed of light should be. In this case, we calculate forward how fast should the mirror rotate. All right, let's see what we got here. So we have a distance here of 35 kilometers and coming back, so we have a total distance of 70 kilometers. And now, previous problem, remember there was something about the Pythagorean problem, Pythagorean theorem. This time around, yeah, we could do that too. We can make here a baseline in the middle, and then there it is. But the thing is that this one here is going to be 35 kilometers or 22 miles, and the rotating mirror is probably in the neighborhood of a few centimeters across. So that means that this baseline here is virtually, absolutely negligible to the total distance here. And it's basically that this hypotenuse is the same as the baseline that I would have here, the adjacent to the angle. And we can see that here as well, that this total distance here from Mount Wilson to Mount San Antonio and back, that was supposed to be a triangle, but it's really just one straight line back, and then it hits the octagonal mirror a few centimeters to the side. So it's pretty much 35 kilometers times 2 is the total distance. So from that one, we would therefore get that the time it takes to go forth and back is 2 times the 35 kilometers per second. 35 kilometers, and divide that by 300,000 kilometers per second. And that gives us the time in seconds. And again, I like the kilometers better than the scientific notation with the meters per second or the 35,000 meters. Okay, now we have to see, well, how fast does this need to rotate? Again, this octagonal side, when the light comes back, has to have rotated just 1/8 of a revolution over here. So the light bounces off here, and then it rotates. This one becomes this surface, and the surface is over here by the time the light comes back. And that would be 1/8 of a revolution, since that one is octagonal. And the rotational velocity, the angular velocity, that was a little too much of an omega. So the angular velocity omega is the number of revolutions divided by the time, which we have determined up here, and that equals then the angular velocity in number of revolutions per second. So I'm going to write here second to -1. When you do that, you come up with roughly 500 such rotations, and that means that this one actually has to rotate really fast, 500 times per second. Now, could you make it slower? No, you can't. Well, I guess you could produce a mirror that has more faces than 8. For example, it could have 16 faces, or you could perhaps make a bigger mirror, but actually that wouldn't gain much. What you could do really is put this further away, and that's already why he chose the other mountain. That's 35 kilometers, 22 miles away, because it's really quite a distance. But he couldn't push it any further, because then he wouldn't be able to see that. That's why you take mountains. He can't just take any spot here. Has to have line of sight between these two, and that was the furthest you can get, and that actually already kicked down the rotation for this octagonal mirror here. Quite a feat, make it rotate exactly 500 some times per second, and then you can observe that light and calculate backwards to get the speed of light here given the other numbers. And again, really quick problem actually. Of course, I like to add some other information into it and make the problem longer than it really is. This is the problem on the heat lamp, and it says a heat lamp emits infrared radiation whose RMS, root mean squared electric field, is ERMS equal to 2,800 newtons per coulomb. What is the average intensity of the radiation? The radiation is focused on a person's leg over circular area of radius 4.0 centimeters. What is the average power delivered to the leg? The portion of the leg being radiated has a mass of 0.28 kilograms. That's roughly half a pound. And a specific heat capacity of 3,500 joules per kilogram in Celsius degrees, which is a little bit less than that of water, but we know we're mostly contain water, so it's relatively close. How long does it take to raise its temperature by 2.0 degrees Celsius degrees? Assume that there is no other heat transfer into or out of the portion of the leg being heated. Okay, I just pulled up this website here where from a company, apparently this selling TDP lamps, and I have no knowledge of these. I cannot vouch for them. It's in a physics book. Apparently, at least the authors think that's a good healing method apparatus. I emailed our EMT instructor here at KPC, but I haven't heard back from him if he's familiar with that. Anyway, as far as the physics is concerned, perfectly fine. Problem actually. Okay, first we're supposed to figure out what the average intensity is. So let's see. I think I'm going to type that here. So part A, average intensity. It's going to look a little better than if I try to write that. And there is an equation for that in the book, which says that the average intensity S equals the speed of light times the permittivity of free space times the electric field squared. And of course this number you look up this time around in meters per second. So 300 millimeters per second times epsilon naught. Do I have that memorized? Well, not really actually. 8.85 times 10 to the negative 12, and then really screwy units on that, coulomb squared per newton and meter squared. So that would be epsilon naught, and then the E is given in the problem in newtons per coulomb, and then when you look at the units you come up with the correct unit for intensity, which is going to be watts per square meter. Then the problem asks for radiation's focus. What is the average power delivered to the leg? So and the average power then, which would be in watts, if you compare this to the intensity here, would then be the intensity times the area. Well, if that area, the square meters here, divides out, and that would be left in watts. And it says over a circular area of radius 0.40 centimeters. So this one here would be the intensity that is just calculated times the area of a circle, so pi r squared, and then the centimeters would have to be converted to 0.04. That was supposed to be a 4. And let's see, how accurate is that? Oh, 10 there. Meters. So convert that first, and then you're going to come up with watts. By the way, this is in the neighborhood of like 20,000 watts per square meter, and this is in the neighborhood of 100 watts. And the third part in here is, again, I'm trying to type this here, the time it takes to heat up that area. And what we would have to do here is go back to a previous chapter on the specific heat capacity, respectively that the heat that is being needed to heat up a material would be the specific heat capacity times the mass times the change in temperature. Okay, one little thing here, one little important thing. This C right here is the specific heat capacity, and that C over here is the speed of light, not to be confused. Why is that happening? Well, because we have only 52 symbols in our alphabet, capital letters and lowercase letters, and we need so many symbols in any one of the sciences that at some point we double up on them. So yeah, make sure that this one here is the specific heat capacity, which is given in the problem. Okay, it doesn't include time, right? But the heat that it would need in order, oops, I meant to go back to black. The heat that it would need in order to heat up by the temperature difference of 2 degrees Celsius degrees is the power times time. That's because the watts is joules per second. So power times time equals then C times M times delta T. And then finally, of course, T equals C M delta T. And these are all given. And I believe they're all standard units, including the mass, which is given as 0.28 kilograms, so there's nothing to convert here. And you would come up with seconds, and it actually says, I have the solution manual in front of me, it's less than a minute that it takes to raise the temperature by 2 degrees, which is 3.5 degrees Fahrenheit. This problem reads, suppose that the police car in the previous example is moving to the right at 27 meters per second while the speeder is coming up from behind at a speed of 39 meters per second, both speeds being with respect to the ground. Assume that the electromagnetic wave emitted by the radar gun has a frequency of 8.0 times 10 to the 9th hertz, so 8 billion hertz. Find the magnitude of the difference between the frequency of the emitted wave and the wave that returns a police car after reflecting from the speeder's car. Which wave has the greater frequency? Why? Okay, in that case, actually, my drawing isn't quite right. The police car should be moving this way ahead of the speeder, and then having the radar gun, I guess, in the back. I picked up any one side for the Doppler effect, so here it is. And there are lots of websites that explain the Doppler effect, and it's really not hard to understand. And you saw it before for waves and sound. So you have here a car, for example, perhaps that is traveling toward the right, that emits some kind of wave like sound or light. And for the observer in the front, that light or sound is being squeezed, the wavelengths, and the frequency increases. So smaller wavelength, larger frequency, and in the back it's drawn out, so longer wavelength and lower frequency. This one here tells me to go to a certain applet, so any applet, there are plenty for the Doppler effect too. So I can have this move here sending out waves, and you see in front of them they're squeezed, shorter wavelengths, higher frequency. In the back they're drawn out, so longer wavelengths and lower frequency. That's basically a Doppler effect, and the rest then is calculation. And again, according to the problem here, actually the police car would have to travel ahead of the speeder. So again, my drawing is not totally reflecting the situation, but we can of course still do the math perfectly fine. So the equation to be used here is that the observer frequency equals the source frequency times 1 plus minus the relative velocity between the two. And when I try to write too small, it doesn't want me to do it, so divided by the speed of light. A couple of things on this one. One thing it says there is if the relative velocity is much less than the speed of light. We saw virtually the same formula earlier for in the chapter on waves and sound. It didn't say anything there as far as the speed of sound is concerned. It has to be much smaller or something. Here they're doing it because soon in a few chapters we're going to go to special relativity, and when it comes to the Doppler effect, the effects of special relativity affect the formula in a different way, and that's why they're saying here that we keep it here in classical mechanics, or in this case optics, and we just say, okay, the relative velocity is much less than the speed of light, and we have a simpler formula that we can come up with. Okay, the other thing that they mention in the problem here, respectively in the text, is the following. The plus sign in this equation applies when the source and observer are moving toward one another, and the minus sign applies when they're moving apart. I had to read through that a couple of times as well. It says further here, the source is moving due east. In an example here, with respect to the Earth, while the observer is moving due east and at a smaller velocity. But let's see, the plus sign is used when the source and the observer come together, and the minus sign is used when they move apart. So it says it actually twice here in the text, and it doesn't mean that they're moving, coming from different directions. It's just that they're closing in towards each other. So they're getting closer to each other. That's when the plus applies. So if they're moving apart, that's when the negative applies. And that would make sense if you look at the positive here. Okay, that would mean that the observer's frequency here becomes larger than the source frequency, and that would make sense if the two are closing in on each other, where the send out wave is being squeezed towards the other car, and then when it bounces back it's also being squeezed because they get closer to each other. So the two the observer's frequency, and then when it goes back to the police car it's yet larger, and that can only be achieved if there's a plus. So that's the way we're going to write it. They come close to each other. Sorry, that was a little bit of a convoluted explanation. I guess I could have done it a little better. Okay. Anyway, plus relative velocity over the speed of light. Okay, now we're supposed to figure out what delta F is, and I can't just take, because it says so in the problem, figure out what the difference in frequency is. But I can't just take the Fs over here because it's a multiplication over there, so I would have to divide, and that's not going to give me a delta F. However, this one will do. If I rewrite this yet again, observer frequency equals Fs, and I multiply this inside the parentheses here, so Fs plus Fs times V relative divided by the speed of light, and then I subtract the two. So I have delta F equals observer frequency minus the source frequency, and that equals the source frequency times V relative divided by C. I don't know what the F0 is, but we're supposed to determine this one here doing this calculation where everything here is given, and if I really wanted to I could figure out what the observer's frequency is. Here I have to see, let's see how they give this here. They give this one here as 8 billion hertz. That's of course 300 million meters per second, and the relative velocity between the two is 39 minus 27, which is 12 meters per second, all in standard units. By the way, the police car is going at roughly 60 miles an hour, while the speeder is going at roughly 90 miles an hour. So when I do this one here, I come up with hertz, and that's the frequency that the speeder receives due to the Doppler effect. And then it bounces back, and actually the exact same equation applies. So when the um, police car gets it back, that total shift, delta F total, is just this one doubled here because the same equation applies. The two are moving towards each other still with the same relative speed. And again, what I'm describing here is that so far what I calculated is just a radar gun's wave being sent out and absorbed or reflected by the speeder, and that's the difference in frequency here, and then it's being sent back, and the same equation applies, and that's why that has to double up as the receiver receives it. So that would be then the total is the frequency with which the car gets it minus the original one, and that equals then twice that frequency that was determined a moment ago, in the neighborhood of a few hundred hertz. Again, this is what's supposed to be figured out, and this one here, yeah, is given from up here. By the way, if you try to determine what the FO, the observer's frequency is, or the observer's frequency on a police car is, this police car, this is the speeder, it's going to be so small, such a small number, subtracted from the source frequency of 8 billion, that it's still virtually 8 billion, but the difference here, that makes more sense to determine that. So a few hundred hertz, as I said, you're going to come up with.